Good morning. I have half past, so I will kick off now. So my name's Stephen. I work at a company called Foundry Zero, which is a small local cybersecurity firm. And my day-to-day job is a vulnerability researcher. And I kind of love all things firmware. So this talk today is going to be a very whistle-stop tour over a bunch of tips and tricks that I picked up along the way of how to deal with acquiring firmware. And then how you might be able to unpack those firmwares so that then you can start doing your vulnerability research or reverse engineering. So a very brief what is even firmware? So firmware is the kind of software logic that makes your hardware do stuff. So kind of everything has got some sort of firmware in it, particularly if you look at the last 10, 15 years, stuff has now become more and more connected, more and more attack surfaces, and therefore the firmware has become more and more advanced. And as I mentioned, I do a lot of this as projects, and kind of in the first couple of days, maybe a couple of hours, but sometimes a couple of weeks, it's my job to sort of tear down bits of kit and try to extract the firmware so that then we can start looking for bugs in it. And you'll notice there's a degree of time there from hours to weeks. That really depends on how complicated the piece of kit is, and whether there's any sort of firmware protection mechanisms that we need to bypass, such as sort of encryption or weird sort of compression that they might do on there. So quick note on here, that sort of kind of true hardware bugs are really rare. Quite often, or for the most part, it's going to be bugs in the software. So an example of this is like the Checkmate hardware vulnerability for older iOS devices, is actually a software bug that's just in kind of a read-only section of Flash. And as I mentioned, firmware is now everywhere. So here's me plugging a USB stick into the back of my lawnmower to go and update the firmware in it. And yes, I did go and fully reverse engineer that firmware, and now I have sort of custom firmware running on my lawnmower. But yeah, that's the world that we live in. That stuff like this. I think the weird one that I came the other day was a new toothbrush that has Bluetooth firmware in it that you can go and update from an application. So it's everywhere. So one of the kind of easiest and first steps that you should do to acquire firmware is actually go and look at the vendor website. These can be absolute gold mines if you're trying to pick a wide variety of patches for a particular device. So go look at the support pages for the particular model you're looking at. There's also a tool that Firmwares have created, which is a part of their scraper, where they've gone and looked at a load of different vendors and gone and sort of built these Python-based scrapers to go and pull down all the firmware on a periodic nature from the vendors. It's worth noting that the tool is out of date for a few vendors, but if you go and sort of look into the tool, you can actually get some key insights of which web servers they might be hosting them on, or are there any other pages that you might have missed? Either are there any international versions of the firmware that you might be able to download? So they're really useful. And I'd also like you to look beyond that firmware download page. So a lot of vendors will perhaps only display the first, the most recent version of the firmware on there, whether that's to kind of make it easier for consumers so they don't accidentally put a vulnerable old firmware, or maybe it's to make my life difficult to stop me from finding those old bugs. So Google sleuthing is one of the first techniques that you can use to get around this. So if you just in double quotes put the model and then do site : and then put the vendor's domain name in there, you can get a whole load of information that maybe in slightly more difficult to navigate pages on their website. You'll get a whole load of junk with press releases and all sorts of stuff, but it might whittle down to maybe 10 to 15 Google search pages where you can look through to see if there's any links on potentially vendor forums that they might have put a beta version out or something. The other thing is archive.org. Go and type in the model web page in there, and then go back in time to see if you can pick up older links. Those links are often stored on CDN servers, so they might still be active, even though they've deleted them from the essentially the front page. And the other thing is looking at other sort of non-HTTP based sites that they might host their firmware on. So a lot of places will use FTP as a backup, even in 2023. So they'll have easy to access FTP servers with anonymous creds that you can go and look in and get not just the model and all the versions of firmware that they've ever released for that model, but also every other model that they've got will potentially be on that on those pages. And once you've kind of reversed some firmware, you might be able to look at some auto-update servers, which are typically different from the kind of consumer portals, because they're meant to be read by their update scripts. And the final thing on this one is looking through changelogs. So you might be able to find a common theme amongst their download links. So this is an example here where they might use the model, the build date, and the build number to construct their links. And even if they've deleted the actual links to their previous firmware, as I mentioned, it might be on a CDN, and you might be able to guess the previous firmware URLs. In particular, like the build dates, you might have to brute force around a few dates to actually get them. So what happens though, and we're seeing this more and more, that vendors won't provide manual firmware updates. So this is where you need to actually go and try and capture those auto-update servers that your devices are calling out to. So in the simplest sense, you connect some sort of laptop or computer in between your router and the internet, and you use a tool, something like Wireshark, to go and see what's happening. So this will get you all the DNS requests, which are particularly useful in this case from your IoT device, whatever it is that's connecting up to the internet, and that might get you some sort of update page that you can go and either browse on your local machine. If you're fortunate, it might use unencrypted HTTP, and then you can actually get the full blobs firmware blobs that are being delivered back down. It's also useful to note that a lot of devices now will proxy their updates through a mobile app. So again, here we've got a mobile app, a mobile phone in the process, so that we can actually capture the DNS requests through there. But of course, what about, Stephen, if they use HTTPS-based firmware updates, which to try and prevent us from capturing them through over-the-air mechanisms? Well, fortunately, developers think TLS is really difficult. So a lot of vendors I'm seeing actually use curl-k to go and perform their firmware updates. So curl-k, for anyone unaware, runs curl in a completely unverified state. So it will ignore any certificate that you provide it and just accept that as a valid one. So that is great for a security researcher like me, because I can go and fake being their update server. So how we go about doing that is very similar to the example above. We go and actually replace our Wireshark instance with something like burp or MITIM proxy. So these are HTTPS interception proxies, which will terminate the TLS connection and then create a new valid connection up to the firmware update server. But that crucial bit in the middle will be completely unencrypted, so you can go and extract whatever's being downloaded through there. So as noted before, it needs to have a sort of a curl-k or equivalent to disable verification if it's your IoT device which is calling out to the update server. I reckon I'm getting about a 50% hit rate on devices at the moment, so it's pretty good and it'll work. But you're actually more fortunate in the case if your device uses mobile devices to proxy those updates, because it's absolutely trivial to go and get your mobile device to go and trust your certificates that you're providing through burp or MITIM proxy. So MITIM proxy is a great example. It provides a WireGuard server, so you don't even need to do any sort of complex NAT rules to go and redirect your traffic through there. And it also provides a web interface that allows you to download a provisioning profile which has your certificate authority baked into there, so it will then just trust your fake update server or the real update server that's got a fake certificate associated with it, and start downloading through there. So now you've captured or acquired your firmware from some sort of website. How do you go about unpacking it? Because a lot of these firmwares will have some sort of compression. There'll be a file system that may have multiple layers of different encoding applied to it to create that one blob. So as a first attempt, there's two really good tools. So there's Binwalk and Unblob. And these tools operate very similarly, where they will detect magic bytes within the file, and then they will try and carve. So they'll try and split up that file into those sections, and then they can automatically extract sort of known file formats. I stress these are good as a first attempt. They do have their limitations. So Binwalk is a good example of like a really basic wrapper around some existing tools for doing sort of the extraction side of things. So those there only really support kind of like the default parameter state for decompression and that sort of stuff. And the other thing with both of these tools is they are confidently successful even when they are completely, utterly wrong. So I had the other day a encrypted firmware that I passed into Unblob, and I wasn't expecting it to do anything. It was a bit of a YOLO attempt. But I was surprised that it had managed to extract a file which was my image name .decrypted. And I thought, whoa, okay, this is good. I'm out of a job. But on inspection of the file, it had done absolutely nothing. It was like byte for byte the same as the original file, and no indication that it had failed any decryption or decompression at all. So do watch out for that. Make sure that you have some reverse engineering skills so that you can actually do sort of format extraction from scratch. So you need to have in your toolset things like UBI reader and unsquashfs, and know how to use those sorts of tools, and also be able to look at your binary in like a hex editor and be able to like see, oh cool, this is clearly wrong, this has clearly got some sort of other mechanism in there. I'm still on the lookout for a really good hex editor, by the way. There isn't one. Vendors be vendors, and they like to do really non-standard things, and this is going to trip you up massively. So I've come across vendors who will use slightly modified compression utilities. So they'll take something that's open source, they'll go and modify it slightly and compile their own tools for it. Now, whether this is for obfuscation reasons or whether it's for optimizations for sort of the embedded hardware that they're going against, I don't really know. I don't have a clear answer on that one, but it certainly makes my life difficult, because then you go and think that, oh, cool, I've got this really nice archive format, I've got a tool that will just extract it, and then the tool will try and extract it and either do a really terrible job, and then you're left with a load of garbled mess, or will just error out. So that can be really annoying. And they also can use sort of custom encryption and encoding schemes. And a lot of these above two things are wrapped in a kind of a post-boot unpacking routine. So there'll be some sort of, I don't know, Linux operating system that will boot up, and then through some sort of init script, they'll actually go and do sort of a second stage unpacking of the firmware. Fortunately, if you can unpack that first stage, then you'll have all the utilities that you can then start reversing and going after those custom compression and encoding schemes. So this is where your standard tooling, Binwalk, Unblob will completely fail. They might try and attempt to do some decompression, and then, as I say, completely fail. So this is where you need to perform your reverse engineering. You need to do some sort of emulation, maybe, to try and extract that firmware using their own tools. You might have to build your own custom tools, custom decompression utilities. And then you get to revel in the success. You might be one of the only people outside of the vendor who's managed to gain access to those binary blobs, which for me, this last point is the most exciting bit of a project, when I get to do something where, I've not just run Binwalk on something and got some nice firmware out. I've actually put in some effort to go and get the raw firmware. So quick note here on handling encrypted firmware. So I've mentioned it a few times in this talk. This can be a real stumbling point. Sometimes the encryption can be trivial, can be like an XOR key that you can really easily figure out, because I'll often leave like 0 bytes all over the place. So you could go and get those keys. But often it will be something that's actually like good encryption. So at this point, the first thing you should do is just Google it. Start Googling like the first magic bytes of the binary blob that you've got, because somebody might have already done the hard work for you, or at least if they've started to reverse engineer it, or for a slightly different older encryption format, they might have the building blocks that you can go and use to expand it and decrypt your firmware. The other thing which is particularly useful to look for is to try and find really old versions of firmware. These may not have had encryption applied to them, or may have had weaker encryption applied. Or sometimes vendors will accidentally leak decrypted versions of their firmware, particularly on forums. That's quite common if they're just trying to get a user to sort of test a new beta version of the firmware. And the other thing you might be able to find is these kind of full install images, which again are designed to kind of install on a fresh system, so therefore they can't have any encryption applied to them. In the kind of enterprise appliance world, you'll quite often get VM appliances or cloud images. These are another really useful resource to try and extract the binaries that you need from them. So these might have the firmware unpackers or the decryption utilities on them. And these are typically, by the very nature that you have to install it on your own VM or in a cloud instance, they're not going to be encrypted. So you need to have a bit of caution here, because the binaries on there might be very similar to what your target hardware is, but they might be like a completely different architecture. So you need to take in mind that when you're looking for vulnerabilities, and it's best to kind of use these as a way of unpacking your firmware for your actual target device. And the next one's a bit of a chicken and an egg. So you want to try and like actually extract keys from a device that you've already got. This is particularly useful. It might not be useful to get the original firmware blob, because you could just get that off the device, right? If you've got the device in front of you. But it might be really useful to actually unpack those set of firmware images for a device, because you might want to just analyze a completely clean image. You might want to try and reverse that update mechanism to see if there's any VONs in it. Or you might just be trying to do some sort of patch diffing, so therefore you want a really clean set of patches for the entire lifecycle of that device. So I mentioned it just there about extracting keys from a device. So how do you go about doing that? Well, you need to find some sort of debugging interface on the device. So one of the most simplest, most common ones is the UART interface, which is a serial interface. This is commonly 4 pins on the device. So you'll have a voltage pin, you'll have a RX and TX data lines, and then you'll have a ground. And if you look at the picture in the top right, so top middle, that would be my first look at, that's probably UART. It would require a bit of testing, but that's probably UART. And although there's 4 pins, you almost never need the voltage pin. You definitely need to find a ground though, but you don't have to use the ground that's next to the pin. I quite often just go to like the RF shields if it's a wireless interface, or like the USB shielding, because that's a lot easier to attach onto. And then once you've found that ground, you can go and find your data lines with a multimeter pretty easily. So once you've connected to that UART interface with a UART adapter, then you may be lucky. You maybe get a root shell. And I'm certainly seeing this a lot on IoT devices, where they put lots of encryption around their firmware and they don't want you to get to it, but they don't think about the close access attack on the devices. They might have a really trivial password as well, which you might be able to guess. If you can't get that, you might be able to get into some sort of pre-boot shell. So U-boot bootloaders might have a pre-boot shell, and then you might be able to use sort of TFTP or something else to actually get stuff off the device. A note here, I was originally going to call this talk how I destroyed a £1,500 vacuum cleaner with 5 volts. Definitely watch your voltages when you're looking at UART. So they'll have voltages ranging from 1.8 all the way up to sort of 5 volts. Test several times with a multimeter before you actually hook up to it. And I recommend using one of these sort of DSD Tech adapters that you can get for about 15 quid on Amazon. So these have a selectable voltage, so you can be sure that you're only going to be putting 3.3 volts in there and not 5 volts. The next thing that I want to highlight, say you haven't got a UART interface and there's nothing easy to attach to. So I've started getting really interested in PCI Express. So I'm seeing a lot more devices that contain sort of a PCI Express interface, and now that might not be what you see in your standard desktop PC, which is a 1 by or a 16 by PCI Express interface. But typically it's things that have sort of modular wireless cards, Bluetooth adapters, or they might have like a cellular modem in there. So those sorts of things will be running sort of PCI Express. But the other thing is some of the microcontrollers quite often have unused PCI Express pins on them that the hardware developer decided not to use. And these are things that over PCI Express you can do something called direct memory access. So this is where via hardware you can actually gain read-write access to the memory that's on the running system. And this will get you access to whatever's running on that system. It won't get you access to the flash storage, but once you booted up the device and it's accepted your PCI Express interface, you can then use one of these special cards. So this here is a PCI Express Screamer. I think this device is the Squirrel. These are about 450 quid, which sounds expensive, but it's actually really cheap for what you're getting. So you're getting a FPGA on here, which does all the PCI Express DMA, and then you get a USB interface that you control via another computer to actually perform those DMA actions. And they're so cheap-ish, even with the Brexit tax here, because these are now being used a lot in online multiplayer games cheating. So it turns out that software-based memory injection technology is being picked up an awful lot by anti-cheat. So therefore, they're moving on now to hardware-based attacks to kind of bypass that. And I mentioned you control it from another computer. You use a program called PCI Leech, which allows you to get that. So one of the best attacks that I use is I try and find something. I dump the running memory, and then I'll try and find something that's going to cause a system command. So ping utilities or other network diagnostic utilities that you might have some sort of web interface for on the device. Those are really good ones to go after. And then you can do a basic sort of command injection through this to spawn a shell, and then you can go and dump whatever you like off the device. So I mentioned that look for all the sort of PCI Express interfaces. It starts getting really messy. So this is a Sonos One on the left-hand side, and we've taken out the wireless / Bluetooth module, which is a mini PCI Express interface, and then we've put that up into a series of adapters that you can get on AliExpress, which gives us there's a PCI Express switch in there, which allows us to convert our one PCI Express interface into two. And then we've got the original wireless card, so we've still got network connectivity and Bluetooth to the device, and then we've got our Screamer on the right hand side, and all of that connects up to another laptop which performs our actual sort of memory attacks on the device. The final point that I want to make here is chip off. So this is where you take the memory chip off the device. You failed all other ways of getting it through sort of debug interfaces. So you have to remove that chip, and then you can read it through external means. I mentioned this as a last resort. This is particularly the case if you're dealing with expensive or difficult to procure hardware. This is quite risky, so you don't want to do it on something that's difficult to replace. So you have to desolder it, and this you need a sort of a hot air rework station. Now this sounds really scary, but it's very similar to cooking chips in the oven. So cooking chips in the oven is 200 degrees for 20 minutes, and that cooks almost anything in the oven. So instead, it's about 300 degrees for 30 seconds, and you just wave the desoldering hot air gun over it, and then the chips will just pop off. That's the easy part. Then the reading part is really difficult. Some devices are trivial. So there'll be sort of your EMCP or your eMMC memory. Those protocols you can easily use like an Arduino or a Raspberry Pi to hook directly into the chip. If it's kind of a raw NAND chip, it depends on the chip, and you'll probably have to get a really expensive flash programmer and an even more expensive adapter to try and access those raw. That can be really difficult. This on the right hand side is us with a small NOR chip. And the actual tool that we're using is called a PC Byte. So this here has a load of very fine needles that you can probe devices. So this is really useful if you're doing anything like this, or if you've got sort of really small pins on the board that you're trying to access UART or JTAG or something like that. So that's a really cool tool. So that's kind of my very abridged version of this talk and very whistle-stop tour. So I apologize for how quick I've gone through that. But like everyone else in the tech sector, we are hiring. If you're interested in getting paid to hack stuff and having a good fun time at the same time, then maybe consider us for your next role. We got 2 open positions for experienced cyber-focused developers and experienced researchers. Thank you very much.